So what we did last time, we did mixed boundary condition for stationary in 2D. So stationary means that it was time independent, and we also we discussed a little bit about adaptive algorithm in 2D. Okay, now today we will move and we start with time-dependent problems, because I think in the second part of the project you are supposed to solve time-dependent reaction diffusion equation. So today we will start with heat equation. And so what we do variational formulation as usual, finite element approximation, and when we have time, we solve some example of nonlinear problem. So this is going to be the plan for today. Okay, so the equation that we are considering today is given in the following way. So dtu minus Laplace u equals to f. It's inside some omega times some time interval. So if I draw it, then our computational domain is some kind of omega like this. It's in space, so this one is omega, and we are solving in time, so that means that we have this type of time axis like this. So we can do like that. Okay, so this one is here x2, that one x1, and here we have a time axis. Then we are going to solve our PDE inside this omega subject to this time. So omega is like this. Something like this cylinder. So here we have omega in the x-axis. Then we have this time. So it moves all the way to time capital T. And inside this domain, so it's going to be space-time domain. We are going to solve u from this PDE, and subject to the boundary condition would be, for simplicity, maybe we can just take u is equal to 0 on d omega times 0t. So d omega means the boundary of omega. So we take the boundary and we just take the whole cylinder all the way until time t, capital T. And we also need initial condition. So initial condition is defined as xt is equal to some given function of x. So this is in omega. Of course, time is equal to 0. All right. So this equation is called heat equation. And when we started, like in 1D case, we were just one example was we have some wire, and we put some heat source. So the right hand side is heat source. Then we wanted to calculate the distribution of the heat in the whole wire. But here it's quite similar. So we have now 2D, some kind of heat source somewhere here, like this heat source. So this is 2DF. It's like a surface, and it is warming up this domain, and we want to see the distribution of the heat when it changes in time. So something like that. So here we should know that U0x F X T are given. So they are given functions. All right, so the usual step that we want to do, this object is of course differential equation. The problem is given here denoted by dE. We want to write weak formulation. Then we want to write finite element approximation of this weak formulation. And finally, we get to linear system to solve. So the steps are the same. And the idea here, of course, we write weak formulation, so to reduce this second order derivative. But so let me turn off my phone. But here, the difference is this function u depends on time as well. So this u depends on space and time. And so far, we know how to discretize in space, because usually finite element, it's a discretization that we do it's in space. But in time, we have to do somehow. So that's what we are going to practice now. Okay, so there is also a different version of finite element approximation that you do also discretization in time right away with finite elements. So then, for example, your problem is in 2D, but since one direction, the third direction will be like time axis, then you could actually construct a mesh, a triangulation of this 3D object. So this cylinder is a 3D object. Then in 2D, your meshes would be tetrahedrons, and you could actually solve it right away inside this 3D object. But this type of space-time finite element, when you do to three space dimensions, for example, in 3D, then one direction would be time. So it's going to be force. So the mesh, of course, there are n-dimensional meshes, but it's quite hard to mimic what does it mean, 4-dimensional mesh. And usually in the applications, therefore people, they do finite element discretization in space. So namely, they take this domain and they split it by finite number of triangles like this, etc. And then once you do discretization in space, you bring your partial differential equation to a form that it is still depending on time. So the time is continuous, you don't discretize on time. So you will end up to ordinary differential equation. So I think we did it in BV3 course, but if you don't remember, don't worry, we will just repeat the same steps once again here. So yeah, to write variational formulation, what we need to do as usual, we take the differential equation and we multiply some test function. At the time being, we don't know what's the space of this test function, and we integrate. So we take the integral in omega, so dtu v plus or minus integral omega delta u v. So there is dx, of course, dx equals to integral omega f v dx, something like this. And now we integrate by parts this part as usual, and we use Green's formula. There will be boundary terms, and the boundary terms, they cancel out because we know we have solution in the boundary. It's u equals to 0. So we choose the test function v to be 0 on the boundary. Then we get this formulation. So we can just write it as a weak formulation. Find u from some space 0, and the space is defined as follows: v xt. You see, like the space that you are looking, it also depends in time. Usually we didn't have this time dependency. These are all functions vxt, so that they are integrable, square integrable. So we usually put this dot t norm less than infinity. So here a little dot, it means that the norm is taking with the first variable. So the first variable is x. So this one is actually the L2 norm for x. So this object is actually integral omega. So it's in x v xt squared dx. So that's the norm is taken in space. And we also require that the gradient of this function v dot t is integrable. And in addition, we require that it is equal to 0 on d omega times 0 to t. So I include the initial condition as well. So we are going to find for u such that, and so now we write integral t to u v dx, and here we do integration by parts. The sign changes, so it's going to be plus integral grad u grad v dx. And of course, the boundary terms, they cancel out because we are going to choose the test function to be 0 on the boundary. And here we have the right hand side, fv dx. That's true for all v from this capital V0 space. Okay, so you see, usually when we didn't have this time derivative term, the rest was just the Poisson equation, and the function space that we constructed, it was independent on time. So here you have to be a little bit careful because the time we are freezing t, and for every t we are constructing this kind of space. So the space we are constructing is actually, they are changing in space. So yeah, so the next step is, of course, for Galerkin finite element approximation, we have to triangulate the mesh. So we of course started by the triangulation somewhere here. You can just triangulate the mesh like this. Something like this. And the triangulation, let me just clean it up here. And we say that triangulation is the set of all K's. So all the triangulars, which are, these are actually K's. All the triangulars we take, and the set of all these K's, it consists of our triangulation. And in addition, we also call this and H is the set of all nodes. So we could just call it like this. So these are the set of all nodes. So inside this triangulation. All right, so we construct finite dimensional subspace of this space, but you see, still it depends on T. So we are doing finite dimensions in space, not in time. So we want to construct VH0, so which is a subspace of V0, and the dimension of VH0 is finite. Something like this. So yeah, there are of course many ways of doing that, and one of the ways we can define this finite dimensional subspace as all functions depending on x and t, such that this v x and t, it's continuous inside omega. So you see, for every t, you freeze t, it's a continuous function in space. That's true for all t between 0 to capital T. And in addition, what we require, v restriction to k is a polynomial of degree 1. So k, this is for all k inside this triangulation, something like that. And the subject for boundary condition is v is equal to 0 on d omega times 0 to capital T. So it's better to write that v xt is equal to 0 for all these, the cylinder, so the cylinder of this domain that we are just constructing in this picture. This is finite dimensional space, in space, of course, because it's continuous. You know, the functions are still continuous in time, but in space, the dimension of this VH 0, it depends on the number of nodal points, all nodal points. Maybe I should just call this all interior nodal points. All interior nodal points. So for example, it's going to be somewhere here, NJ, something like that. Yeah, now I think we can write our finite dimensional weak formulation that we usually refer to Galerkin fem. It's find UH from VH0 such that the following formulation holds. So integral dt UHV dx plus integral nabla UH nabla V dx is equal to integral FV dx. And that's true for all V for this finite dimensional subspace. Okay, so if you just look to this operational formulation, I mean, there is nothing new except the first term. So how to deal with this time derivative? Of course, if you recall what we did in Scientific Computing 3 course, you already know how to deal it. But here, first of all, we are doing in 2D, and then we want to extend the same methodology for some nonlinear problem. That's the aim that we want to do. So if we go back to this schematic scheme that we usually write, so here we started with the differential equation, we did variational formulation, and now we did Galerkin finite element approximation, which is finite dimensions. The next step is, of course, to construct linear system, corresponding linear system to this peak formulation. So as usual, since UH is an element from this VH0 space, then there exist coefficients so that these nodal points, they belong to these interior nodal points, the set of interior nodal points, such that we can write this UH T as a linear combination of all these coefficients, and this is the key point. So the coefficient depends on T, and the test function there depends only on space. So something like this. So if I just come back quickly to this figure, of course, we do the triangulation, and for every interior nodal points, we construct a head function, but that head function, they are independent in time, so they are constant in time, but they change, of course, in space. So I think it is quite hard to draw here, because if I put the head function up, then it looks like I'm putting up on time, but in reality, the head functions are constant in time. So does this mean that our mesh will be constant in time? I didn't understand your question. So in this construction, the mesh is time dependent. What do you mean? The mesh doesn't change in time, but you have a valid question. In some cases, mesh also changes in time, but that's not the case that we are considering here. If mesh changes in time, then you will not have this kind of cylinder shape. For example, let's say that you're simulating a bubble which is moving inside some channel. So this bubble, of course, changes in time. And if you mesh, your mesh is like a surface of this bubble. So of course, that's going to be time dependent, but not in this case. In this case, the mesh is just constant mesh. It's only a fixed mesh in space. It's not changing in time. But if you mean, how do we take care of this time level? So we are going in a while, because once you fix the mesh, then you discretize in time, but these meshes would be just flipped, for every discrete time, then you put one mesh. In any discrete time, you put another mesh. So you just move this mesh in time just constantly. So we insert this formulation, so this representation of this unknown function to the finite element equality here, variational formulation. And we're going to rearrange a little bit. For example, the integral, I put it inside, and summation, I put it outside. And this size, since they depends on time, and here the integration, it's only spatial integration, then I can just move these coefficients outside of this integral. So in other words, we are getting this system of equations. So sum and J is from this set of interior points. So here we have dt psi j of t, because psi depends on time. And if I take the time derivative of everything, so here it's going to be time derivative because it's depending on time, but phi is not depending on time. That's why it just pulls out from the time derivative. So in other words, if I do time derivative of psi j, if I j, it's going to be phi j time derivative of psi j, because psi j depends on time, not the phi. So therefore we get integral here, and inside the integral we have the usual phi j's of x, phi I of x dx, and the second term would be plus sum nj from this interior point. And here we have again psi j depends on t, integral nabla phi j depends on x, nabla phi I depends on x, dx is equal to integral omega f phi I x dx. Of course, this f, it depends on space and time. So f depends on space and time. It's a function that changes in time and space as well. So this equality is true for all nodal values inside the set of these interior points. All right. So now we just we do the usual stuff. We denote this integral by m. It's a mass matrix. And now here, since it's a partial derivative of psi, which only depends on t, and usually this is just equivalent to ordinary derivative. You can just write it d psi dt. So it's just ordinary differentiation in time. And so let me move this object a little bit down. Like this, I can put it, and I put it here. Then this part is the usual stiffness matrix A. That part is our unknown vector, but it depends on t, of course, here. And the right-hand side, f is known, phi is known. The whole function is going to be a function, a vector, depending on time. Okay, so it doesn't depend on space because you do integration in space and it's a definite integral. It's going to be one number. The whole thing, everything is a function of time. So if we just rewrite what we get, we obtained the following equation. So m times d psi dt plus a times a times psi. I can just write the argument just to make sure that we got rid of one of the variables. It was x, but now the equation that we are writing, it has only one variable. It's going to be depending on t. That's equals to b on time t. Okay, so now we got, we had the PDE and the differential equation that we had before. It was a PDE, partial differential equation, but this equation that we got, it's a system of ODEs. System of ODEs. System of ODEs, time is changing from 0 to capital T, and we have to define boundary condition or initial condition for this T. So that is the subject here would be psi 0 is equal. Now I call this U0. I call this bar. So we have this U0 is given function, but U0 bar is, it's like a long vector. So for example, it says that psi J0 is equal to U0 at nodal value J. So it's evaluated at this nodal value. Yeah, so U0 is initial condition that you are given. So you are just, it's a function, it depends on the nodal values. You just constructed the initial condition for this ordinary differential equation in this form. All right, so we got the system of ODEs, and now we can use any favorite time stepping scheme in time, if you like we can do a forward Euler, backward Euler, Crank-Nicolson, for example, or Runge-Kutta schemes. Then the idea would be, now it's a system of ODEs, so the number of equations are equal to the number of interior points in the mesh. So that means that for every this point here, so let me just draw it in. For every point, the ODE gives some solutions. So the solutions would be some kind of like this. It changes in time. So for every point, changes in time. There are many points here, etc. So then eventually what you come at final time, you will get the solution, discrete solution of given points, so corresponding to the mesh that you are giving from the ordinary differential equation. And if, of course, if you can solve it analytically, you are fine, you can just solve it. But yeah, in practice, we want to approximate it as well with some kind of time stepping techniques. All right, so do you have any questions so far? So if there's no question, now let us discuss some discretization in time. So we got the ODEs, and we have to do some kind of discretization to discretize this time derivative. So that's an aim that we want to do. So you could just take any literature and implement some kind of time stepping, like forward, backward Euler. But so let us discuss how could we use some of the information from finite element analysis in approximating this time derivative, for example. So maybe not in approximating time derivative, but these functions, because these are continuous functions. For example, if I just draw it, time interval, I draw it like this. So this is our time interval. And function psi, or let me just call for the time being like function. There is some function changing in time. So this function psi could be also continuous function in time. And what we want to do, of course, when you solve it, you will get this kind of continuous function. But we want to find some discrete solution. And the usual stuff that we do in finite element. So we start from time 0, and we go all the way to time capital T. And we split this time interval by a finite number of small subintervals. So this is like the usual stuff that we do in finite element. And hopefully, we approximate the values of these functions. So let me just call this function u of maybe w of t. We want to approximate the value of this function at given points, something like that. And yeah, so if this point is tn plus 1, and this one is tn, of course, time is t0 is equal to that, and so on we go. One of the easiest way, or one of the, not easiest maybe, but one of the convenient way that we know in finite element approximation from this course, how to approximate this curve line inside this interval with some kind of polynomial space. So of course, then you can quickly say that we can just take the interpolant of this curve line. So the interpolant, linear interpolant would be something like this straight line. And this is going to be pi h w. So it's a linear interpolant of that. So if you find this linear interpolant, of course, you can next approximate all these intervals by this linear interpolant, and it's going to be one of the approximations that you can find. For this continuous, it could be very smooth, it could have many derivatives of this function depending on t. So how to construct this interpolant now? So this pH, how to construct it? So this interpolant, of course, depends on time. How do you construct it? We just use the same idea we did it in, I think, the first lecture that we did. So we want to construct P, maybe we can just say it, we want to construct linear interpolant. So linear interpolant would be one of the easiest, but if you want to make it high accuracy, then you can just go to higher polynomial spaces like quadratic, cubic, etc. So if you recall what's the definition of interpolant, so function PHW is interpolant of this W on this interval, so Tn plus 1, if the value of the interpolant on this Tn is equal to the value of the function in Tn, and also the value of the interpolant at Tn plus 1 is equal to the value of the function at Tn plus 1. So it's actually a definition of interpolant. Something like this. All right. So, and in addition, we know that linear interpolant can be written by using Lagrange basis functions. If you recall what we did, so we take these two basis functions here like that. So we call these basis functions, let's call it lambda n. The other one is lambda n plus 1. And we can write the interpolant in terms of basis functions. So it's a linear combination of these basis functions with the nodal values of this unknown function that we are trying to approximate. So here we get pi h wt is equal to lambda nt wtn plus lambda n plus 1 t wtn plus 1. So it's just a definition of interpolant. And you can quickly check that if t is equal to tn, then lambda n of tn is 1, but lambda n plus 1 of tn is 0. So the second term disappears, and we get to this first condition that we get for the interpolation. And if lambda n plus 1, and if we put the second point here, then the second term, the first term is 0, so we get the second property that we had. So, and in addition, we also practice a lot how to write the equation of this line. So the equation of this line, so here on the top, it's equal to 1. So what we usually do, we take t minus tn plus 1 divided by this size. So let us call this size k. It's a time step. So k is a time step. And then we can rewrite it. It's going to be like t minus tn plus 1 divided by minus k, because tn minus tn plus 1 is going to be minus k. And here we have wtn plus, now here t minus, so here now t minus tn. So we have to take the other point divided by k. So tn plus 1 minus tn is going to be mesh size, time step in this case, wtn plus 1. This is what we get. And let us write the first term, this object. Let us consider that object. I will just rewrite it. It's going to be t minus tn plus 1 divided by minus k. So it's equal to t minus tn minus, no, plus k. Because you see we have tn, we add k, and we end up to tn plus 1. So there's a relation between tn plus 1 and tn. You can write tn plus 1 as a sum of tn plus k divided minus k. That is equal to t minus tn minus k divided by minus k is equal to, now I divide k by k. So it's going to be 1 minus t minus tn divided by k. Right? So it's just a simple algebra we did. So we can write it here like 1 minus tn divided by k wtn plus t minus tn divided by k wtn plus 1. And the last point that I want to mention, so we can call this guy theta, and this, the whole bracket that we had, the first one, it's going to be 1 minus theta. And we get the following relation. So it's going to be 1 minus theta wtn plus theta wtn plus 1. And here 0 less or equal to theta is equal to 1. So it's some constant between 0 and 1. Okay, so now what we did here is, it on the left we had this linear interpolant, so pH wt, and on the right we get some kind of relation. So it's a relation between the nodal values. So here is a nodal value. Just write it. This is wtn, and here is also wtn plus 1. So we discretized. If you find some theta, so we can just pick theta between 0 and 1. So that means that this line we could just discretize with the nodal values of these functions at given this time interval. So the idea would be, we have to use it here. We have to discretize time by finite number of intervals. Then for every time, so it's going to be t0 equal to 0, t1. So somewhere here we have tn plus 1, etc. So in every time level, we need to use the value of the function at time to write our approximation. That's a aim that we want to make. So maybe, yeah, we can just stop here and continue after the break if you don't have any question. If you have any question, just go ahead and ask.
Yeah, I have a question.
Yeah.
So if you scroll up a bit to when we derived the linear system of equations for the time independent, or the time dependent, yeah, right there. In the bottom there, it's really similar to like the material derivative. Is that a coincidence?
You mean The
So-
material derivative, isn't it a bit different, material derivative?
But there's things that cancel out when you, so I just did it by paper, and there's things that cancel out. And like if you do the material derivative of psi times the mass matrix,
Mm-hmm.
then you get the same result on the left-hand side.
On the you mean this one?
No, the A term as well, because M and A are related through the gradient, right?
Yeah, there's a gradient here.
Yeah.
Yeah, it is not a coincidence. I mean, material derivative is obtained by some kind of conservation laws, right?
Mm.
So yeah, you just
Yeah, it's just a little thing that I noticed.
yeah.
Okay.
Any other questions? So if there's no question, let's take a break and we come back 12:15. No, 2:15 in 15 minutes. And yeah, so we did triangulation, meshes, finite elements in space. Once we do in space, of course, there will be a lot of integrals, but once you calculate these integrals, they are just numbers. And therefore, the space dependency in the differential equation, it disappears. So it's going to be a bunch of numbers, which counts as a coefficient to this ordinary differential equation. So the equation depends on time. And we say that we need to do some kind of time discretization to solve it numerically. And what we did, we say that if this psi function is some kind of continuous function in time, then we could approximate it by using some kind of linear interpolation. So it's finite element linear interpolation. And here we use the definition. Definition says that the linear interpolant in this interval is a linear combination of the basis functions of these intervals. So it's going to be lambda n and lambda n plus 1. So here we wrote the linear combination. We used the definition of basis function. We wrote it. And we got this type of relation. So if you look back to the differential equation here, so I saw that in my notes, I wrote there is one misprint here. So I wrote Tn, it should be Tn plus 1, but here I write it correctly. So what we say that we use this idea and we approximate this psi t, because we have a psi t in our differential equation. We approximate it by this relation that we get. So this is psi at time n plus theta psi n plus 1. So here we denoted that psi n is the value of the function psi at time tn. So this is like we are doing discretization in time. So in every time interval here on the nodal values, we denote the value of the function at given nodal values as wtn here. So it's actually, according to our notation, it's equal to wn, something like that. Then, yeah, we come back to the ordinary differential equation where we wrote it here. So this psi, we approximated with theta-related equality. The right-hand side beta, we also write in this relation. And the time derivative, we can use different schemes to approximate the time derivatives. And in this node that I wrote, I just use simple forward Euler. So we will get that relation. So we use forward Euler to discretize the psi dt. So it is equals to psi n plus 1 minus psi n divided by k. Kn. So Kn is the time step, of course, can change it, but Kn is a time step between Tn plus 1 minus Tn. So time step. Yeah, we can just move it here, time step. All right, so then we have the following discrete problems. So psi n plus 1 minus psi n divided by Kn. And instead of psi t here, so instead of psi t, we are going to write this relation, this approximation with linear interpolant. So it's going to be A. So inside the brackets, 1 minus theta psi n plus theta psi n plus 1 equals to 1 minus theta bn plus theta bn plus 1. And we are going to solve this scheme for given psi 0 is equal to psi 0 at time 0. Then we iterate for n equals to 1, 2, etc. Because it's a time discretization, we do it in time, and we just, when you put n equals to 1, so we have to recover the initial conditions. So I include time 0, n0, because when I put in n equals to 0, so here it comes psi 0. This one will be psi 1. Then we have to use this value at point psi 0. It's the initial condition. We bring it here. So this will be psi 0, psi 1. And the right-hand side is, of course, you can evaluate. It's given function. And this scheme that we constructed in the literature, it's called theta scheme. Because it depends on theta, and by the construction that we get. So here, what we defined, this construction that we get, theta changes between 0 and 1. And many numerical schemes, of course, you can construct it by changing this theta. For example, so when theta is equal to 0, then the scheme becomes psi n plus 1 minus psi n divided by kn plus, so 0, that term disappears. Here it is 0, it's going to be just psi n. And on the right-hand side, that term at time n plus 1, it disappears. So here we get A psi n equals to B n. And you see that this value is known, that one is known, the right-hand side is known. And you just solve psi n explicitly for given values for all n equals to 0, 1, etc. And this scheme is called forward Euler scheme. Yeah. So with the same way, if we put theta equals to 1, then the first term disappears. So we are getting theta is 1. We are getting here term psi n plus 1. And on the right-hand side, this term disappears, depending on time Tn is going out, cancel out. Then we will have this Bn plus 1. And the resulting scheme that we get here is going to be psi n plus 1 minus psi n divided by Kn plus A psi n equals to B, actually plus 1, n plus 1. And here we see that the only term which is known for n equal to 0, 1, etc., it's this term. So the rest, you have to solve it. And in every time step, of course, you have to solve a linear system. And this method is usually called backward Euler method. And of course, there could be many cases, but one of the cases that we consider in the project is psi equals to 1/2, then you will get theta n plus 1 minus theta n divided by kn plus 1/2 a. You see, if this one is 1/2, it's going to be 1/2 here. Theta is 1/2, 1/2 here. You can pull out 1/2, or maybe you can just, it's better to keep it. So it's better to keep it here. And psi n plus 1 plus psi n divided by 2 is equal to bn plus 1 plus bn divided by 2. It's the average of the solution at time tn and tn plus 1. And the scheme is, of course, is true for n equals to 1, 0, 1, etc. And this scheme is usually referred to as Crank-Nicolson scheme. Right. So I think from the basic courses, we know that forward Euler is first order. So we just write the order like this. Backward Euler is also first order. But Crank-Nicolson, since we are taking the average, you can do von Neumann analysis, for example, the one you learned from BV3 course, and you can prove that the method is actually second order in time. So the method is second order in time. And but if you look to the finite element discretization, so we did finite element discretization to construct. Oh, so I'm missing a matrix here. So you should see, you should also help me. So there is matrix. Let me just write it. There's a mass matrix I'm missing, because the scheme comes with a mass matrix. So there's a mass matrix here. The mass matrix is here. So what I wanted to say, when we do this finite element approximation, we do mesh and all these polynomial spaces in space, and we construct that. We use that in construction, the matrices M, this matrix A, and the right hand side vector B. And we know from finite element analysis, at least when we do some a priori error estimates for a simple case, the optimal convergence rate for the Gagliarkin approximation is second order in space. So, so the overall error would be second order in space, like this. And here is also second order in space. But since you are doing first order in time, the overall order of this scheme is going to be dominated by a time error. It's going to be just first order. But for the Crank-Nicolson scheme, then you will have overall second order. So that is second order in time and space. So in the project, you are going to implement second order Crank-Nicolson scheme. So hopefully you will get some high accuracy in time and also in space. So we are going to do stability estimate, I think, next time. And we can actually show that forward Euler, it will be conditionally stable. So you have to choose the time step small enough for the stability. Backward Euler will be always stable. It's implicit scheme. and Crank-Nicolson will be also stable all the time. So this is something that you can use your knowledge from BV3 course, or we can also, I think, 1 or 2 lectures we spend on the stability estimate. We want to make sure that time stepping and doing with finite element and also some kind of theta scheme is stable, so we can solve it in time. All right. Is there any question? So if there's no question, I want to solve some nonlinear problem. I want to show it. And hopefully this will be used. One of the exercises, one of the problems in the project is nonlinear reaction diffusion equation. So you can use the same idea there to discretize and write the code for that. So it is nonlinear reaction diffusion problem. So reaction, we know that heat equation is actually diffusion problem because we have second derivative term in space, and reaction term is a nonlinear term which is included in this form. So the equation we are solving in time plus u square is some reaction coefficient minus the diffusion term is equal to f. So it is in omega times 0 to capital T. And you can use many different boundary conditions, but for simplicity, I'm putting 0 on the boundary. So it is on the boundary and the whole domain. And also we have some initial condition. So time 0, we are giving some function which is independent in time. So it is in omega T is equal to 0. So this term is usually referred to reaction term. And the other term, this term, is diffusion. So the equation is called reaction diffusion equation. So diffusion is like physical product. Maybe many of you know better than me if you have a physics background. Of course, I am not a physicist. Diffusion is like a process that diffuse, it models diffusion. So for example, heat transfer, if there's a diffusion, then it will just collapse. So it's going to be heat distributed in the cold room or somewhere. Reaction is, it exaggerates some process, so it's quite non-linear. You will also see in the project that if you turn off the reaction term, your solution would be just, eventually it will collapse, it will go to 0. But with the reaction term, some kind of chemical process is involved. So then, you know, continuously you get some add on to the solution, so you will get some complex behavior with the nonlinear term. So how to deal with this nonlinear term? Because we cannot put, if we just put here UH equal to this linear combination xi j phi j, so it's a sum, right? The square of the sum is going to be really complicated nonlinear term, and usually it is not possible to bring it to the linear system. So the idea is we have to pass all the steps from the differential equation and we want to come to the final linear system to solve. What to do? Yeah, so again, this was our differential equation. We have to follow the usual steps: differential equation, weak form, Galerkin finite element, and finally this linear system. So for the time-dependent problem, of course, this linear system would be time-dependent. It's going to be a linear system of linear differential equations. Then you have to do time stepping as we did it here. Then for every time level, you have to solve linear system. So weak form, I'm not going to define the spaces. They are going to be the same spaces that we defined earlier for the heat equation. So we find the weak form in this way. So find U from V0 such that integral dt uv dx plus u square v dx plus delta u delta v dx is equal to integral fv dx. Like that. So that's true for all v from this V0 space. And we follow the same procedure as we did before. There's a triangulation, there's a mesh. We construct the finite subspace of this, this space. And then we write the weak formulation in the finite dimensional space. So it's called the Galerkin finite element formulation, which reads find UH from VH0 such that this formulation holds for this UH instead. Yeah, the weak formulations are the same, but this one is finite dimensional case of the usual weak formulation. So now you see, like when we come to this step, the next step would be, of course, we say that the UH is a linear combination of unknown coefficients. So for all j's from this interior set, xi jt phi jx. We usually did that for the linear problems. So we could insert this here and we can rearrange and pull out this xi. So xi is unknown. So it's going to be mass matrix times xi here, time derivative, of course. That's also a linear term, that's fine. But what to do with this nonlinear term? Because here is u square. If you put square for both sides, so square here and square there, it's a long sum square. It's going to be complicated, and you cannot construct a linear system in this case. So we instead we have to do some trick what to do with this linear term, and there was a suggestion in the project that, so let's call this term, this linear term, I call it S. So S is UH square. Again, we use this the trick. So let's say that in 1D we have a domain and we split it by a finite number of points, and S is a nonlinear problem, something nonlinear function, something like wavy function, and we cannot construct this S analytically, but we can interpolate it. So our famous approximation is just interpolation. So in this case, the easiest one is, of course, linear interpolation. So here we want to construct PHS so that it interpolates capital S. So the good thing with this interpolation, we have an error estimate for the interpolation. If you remember, we can say that if S is known, the difference between this interpolant and the exact function, it is approximated, it is estimated by H square times S square, you know, S double prime. So if this one is quite smooth function, we know that the convergence of this red line to the blue line is at least quadratic, so it's really high accurate. There's a convergence property, we can do it a priori for the interpolant, and that's why we can use it, because eventually in finite element, we start with some mesh and we do mesh refinement. When we do mesh refinement, then this type of approximations, we do it more and more accurate. And again, if we use the definition of interpolant, the interpolant is an element from finite element space. So it's an element from finite element space, and therefore, and also the definition of interpolant says that the function matches, so interpolant, of course, it depends on space and time, is equal a linear combination of basis functions, but the nodal values is a value of the function at given points. So it is tj's, phi j's. So let me just make it a little bit clear, because S depends on, so let me just call this one Sj, and phi jx, so obviously Sj. I want to take it depending on time, because the left-hand side is a function space and time. So in other words, it says that this function red interpolates function blue if at the nodal values, so these are the nodal values, they match, so they are exactly the same. Therefore, in these nodal values, we take the weights are just this nodal value. So it's a nodal value of the exact function at given point nj, and we just take a linear combination with the basis functions. So, but we know that S was U square, or in fact UH square, and therefore we know that UH at the nodal values, if I just take it UH and a nodal value, so it is actually psi at the nodal value. Yeah, I mean, if I just freeze time and I define these coefficients on time, I mean, because the basis functions, we know it in space, but I'm constructing this UH, I'm taking, what does it mean in time? So these coefficients, this size in time, of course, they are like, I can just write it. If I look at it in time, so it's just the value of these coefficients in time. So these two relation, it gives that Sj in time. So this object is actually psi j in time square. So now we can, because these are just one numbers, since they are just one numbers, we can just calculate the value of Sj, it's the square of that number. Then we write the interpolant, so PHS in time, I write first space and time, is equal to linear combination. So Nj from the set of nodal values, interior nodal values, psi j square t phi j x. Then in this, in the formulation that we had here, so then you change this by integral interpolant of s. Instead of taking this continuous s, you just approximate it by its interpolant values. So if you do that, now we can insert the sum here and also the interpolant. The interpolant would be defined in this form, so we say square. And we have the following formulation. So let me write it and we will discuss. So we get the mass matrix times, yeah, we have some time. Maybe I can just write one. So we have sum and j's from the set of interior nodal values psi j d dt of t integral phi j phi I dx omega plus the second term now. So nj in these nodal values. So we have this nonlinear term, but we pull out this coefficient. It's going to be psi j square t integral phi j phi I dx. And the third term is the sum nj from the set psi j integral. It's a stiffness matrix. And this is equal to the right-hand side vector. All right, so this formulation is true for all ni's from the set of these interior points. And we can quickly see that this is the usual mass matrix. That one is also mass matrix. But here it is stiffness matrix. And this one is like right-hand side. And we get the following system of equation. M dxi dt plus m xi square plus a xi equals to b, subject to the initial condition at time 0 is u0. I just put the bar like this. So with this simple trick that we did, and we approximated the nonlinear term with its nodal interpolant. We got this linear system of, this system of nonlinear ordinary differential equations. So I should, so this is system of nonlinear ODEs. All right, so I think the easiest way to solve this, for example, if you do Crank-Nicolson, you can just put this nonlinear term, you can linearize it from previous time step. So one example. So it says that linearize the nonlinear term. Using previous time steps. So what I mean, if I just use Crank-Nicolson here, for example, so Crank-Nicolson, then we have m psi n plus 1 psi n divided by kn, and this part I linearized from previous time step, so it's going to be plus m psi n square. It's a pointwise. You see, like it's a not scalar product of the vector. It's a long vector, so each component of the vector is squared. I think in MATLAB you just write it xi dot multiply xi, something like this in MATLAB. Then we have plus a xi n plus 1 plus xi n divided by 2 equals to b n plus 1 plus b n divided by 2. That's true for all n0, 1, all the way until the last value we get it in time. All right, so here you see that this value is calculated from previous time step. That value is also calculated from the previous time step. That one is calculated from the previous time step. And if you just simplify it on the left, so everything I multiply by kn, and we have this equation on the left. We have m plus 1/2 kn a times psi n plus 1. And on the right, we have, so there is m times psi n with the negative sign. We put it to the right hand side, it's going to be positive. Here we have a times psi n, but with positive signs. On the right hand side, it's going to be negative. We have m minus 1/2 kn a psi n. And we have this term as well. So plus kn m psi n square. So I wrote it in this form. So let me just write it. Psi n square. All right, then we have
minus.
This. Oh, there's minus, exactly. There's minus. I put this to the right hand side, it's going to be minus. So let me make some space here. And then I have the right hand side contribution. So this is kn divided by 2 bn plus 1 plus bn. And that's true again for n equals to 0, 1, and etc. All right. So in the lab, you already learned how to construct stiffness matrices. I think there is a script also in the book. And there is a script also in the book how to construct the mass matrix. And when you solve the Poisson equation, you also learn how to construct the right-hand side. So you already have all these tools. The only thing that you have to do now, you have to solve this equation. So in every time step, you fix the time step psi 0, so when n equals to 0. You calculate the right-hand side. These matrices, you already have it. Then you solve this linear system by backslash. So this a new matrix, you solve psi n plus 1 is equal to that matrix backslash the right-hand side. You update your times because you solve it for psi n plus 1. Then you do iteration. You solve for the second, third, etc. So it's going to be solution to the time-dependent reaction diffusion equation. Okay, so I stop here, and I would be happy to answer any question you have it. Please unmute yourself and ask question if you have.
Yeah, Murtaza, I had one question of actually way earlier when you were mentioning the order of convergence of these numerical methods. And then you said that in space, finite or Cayley-Orkin finite element method has order 2 convergence. So, I mean, I am assuming that that means that in part B, the first question in the project, it asks us to numerically calculate this order of convergence. So then I'm assuming that there we should get a 2, and if we don't get a 2, we're doing something wrong.
So this order of convergence in the L2 norm.
Okay, because in energy norm, there's something different, right?
No, in energy norm, you get 1.
Okay, perfect. Okay, yeah, that was my question, because it was really weird. Because in the labs also, there were, like, if you follow the exercise, I think you got a 1, and then there was in the paper something about getting a 2, so it was a bit confusing, but okay.
Yeah. So it all comes back to this interpolation estimates. So if we recall, we have this estimate, F minus PHF is CH square, right?
Yes.
F double prime. So this is one estimate. The second estimate is if you have a derivative PHF prime.
Okay, so that is the energy one. Okay, and it's an H normal H.
Yeah, there's only one H.
Yes.
So actually, this one is energy norm in that case.
Oh, okay, there you go. Okay, that answers my question.
Yeah.
Thank you very much, Murtaza.
Yeah, you're welcome. Any other questions?
I mean, now that I asked, I mean, we are also supposed to get, well, even if B has this index n+1, right? Since B is known, we can still compute it. It's the same thing as Bn, but with another time.
Of course, because Bn depends on F, right?
Yes.
Bn depends on F, and F depends on time. So Pi is integral F, what is this, Ti, and I think the index comes, how is it? So it is F phi I x dx, of course, this one. But this one is function of time, so time and space.
Yeah. Okay. So then we are also obviously expected to make, so the load vector function will have to change as well.
Yes, definitely. Okay. It changes in time.
Okay. Thank you.
Of course. Yeah. If F is stationary, if it doesn't change in time, then it will just stay constant. But in general, it should change in time. Okay, any other questions? So if there's no question, I stop here. Thank you for today, and I see you tomorrow then.